Hello, hi. Hello everybody, welcome to my talk. I'm Petar Zecevic. I come from Zagreb, Croatia, from a company called SV Group. We are 40-something people. we provide consulting services. We sell hardware and software, and I work mostly in big data field. I'm also organizing Apache Spark Zagreb meetup group. Used to be monthly, but now not so much. And I wrote Spark in Action book. At the end of the lecture, I'll be giving away 3 ebooks, so stick around until the end. We'll play a little game. And Manning, my publisher, provided us kindly for this conference with a discount code for 40% off all Manning books. This is a sample from the data section. You can use this code when you do the checkout, if you'd like. So, agenda for today, I'll talk briefly about Spark, about architecture and so on. And then I divided some kind of tips and tricks for Spark into Spark Core, SQL, and streaming, based on my experience from our projects and based on my research for the book and so on. So, I don't think this has much sense because I don't really see you. Normally, I like to know who I'm talking to, but I'll skip this part. So, what is Apache Spark? It's a distributed, general-purpose, large-scale data processing engine. Distributed means it's running on many machines. It's running in a sort of a cluster. The computations are parallelized on those machines. It runs in parallel, and program is sent to the data. Instead of sending much larger chunks of data to the program, so it's much more efficient to serialize the programs and send them to data. It's general purpose, which means it can be used across industries. It can read any kind of data, write any kind of data. Basically, whatever you can do with Java, Python, R, Scala code, you can do with Spark. Instead of, because of some architectural limitations, you cannot have access to GUI or your screen or something like that. It's large scale, so we all know about those monsters, huge social networks, but there's also large scale in other industries like banks, healthcare, biology, telecommunications, and weather, astrophysics. There are huge telescopes that's streaming huge amounts of image data. But it should be noted that you should have enough data, because if you're, these days, the machines keep growing, and it just might happen that all of your data fits into a single relational database or single machine. So if you write a clever set of Linux scripts or C# programs or Java programs, you might have better performance than using something like a distributed engine like Spark, because there's always some overhead with orchestrating work in a cluster. So it might be slower if your data fits on a single machine. And it's a data processing engine, so it's not an ERP system. It's not for storage. Spark stores data temporarily in memory and can use other storage systems to store data there and read data from those. But it's not a storage per se. It's not for OLTP processing, online transactional processing, for OLAP processing, for analytical processing, batch processing, and so on. It's not good for doing small updates in a transactional settings like RDBMs do. And it's not for reports, visualizing things. It's good for preparing data for visualizations, but not for visualizations themselves. Why would you use Spark? Because it's fast. It's getting faster with Project Tungsten. If you know, if you keep track of what's going on with Spark, since 1.6 it has Project Tungsten that increase the speed even more with off-heap allocation and so on. It has simple and concise API based on Scala and Python with functional programming paradigms. It feels like you're handling local collections of data, but they're in fact distributed, and it's kind of easy way to program. It's a unifying platform, which means it has a lot of different types of functionalities built into it out of the box. I'll cover them briefly. And today it's really gone mainstream. It's sort of replacing maybe Hadoop, MapReduce. It's a part of all the major Hadoop distributions, and it has been integrated into many different products. For example, IBM's products, they have been integrated inside their programs, and the community is huge, and so on. The development that's gone into Spark is great. So the basic architecture is that you have a driver, JVM, your client JVM that's running the driver process, and the driver or the Spark context object is responsible for allocating a set of executor JVMs from a cluster manager. And that cluster manager can be whether Yarn, Spark standalone cluster, Mesos, or most recently, Kubernetes also is now, I think, already supported as an execution engine for Spark. So each of the executors has a certain number of task slots, which are just threads running on that JVM, which you can limit by parameterizing Spark. And each executor has some amount of JVM heap, and also now off-heap storage, also their direct process memory. And in this example, all those executors could be running on 5 machines or a single machine. This is just a logical picture. So the components of Spark's API you work with there's Spark Core, where you work with RDDs, resilient distributed data sets, which are distributed collections of data. And there's also, in Spark Core, there's those functionalities for distributing, organizing work inside the cluster, communication with the executors, and so on. Then you have Spark SQL, and Spark as a whole has been moving to SQL, which is handling data frames and structured data inside data frames, where you have rows and columns, and you can use standard ANSI SQL queries to query the data and process it. Then you have Spark Streaming for handling real-time data, Spark GraphX with graph algorithms, and Spark MLlib library with most of the often used machine learning algorithms. And all 3 of those GraphX, streaming, MLlib have been moving to SQL. So you have now graph frames, which are based on data frames. You have structure streaming, also based on SQL, and they ported all of those older versions of machine learning algorithms based on RDDs to data frames counterparts. So the tips and tricks based on core. So I'm going to start with the basics. You should cache data. Spark is known that it can cache data in memory and reuse it over and over again if you need it. So if you need to reuse an RDD or a data frame more than once, you should cache it. Otherwise, in this example, you have you read a text file, cache it, and then do something with the data in 2 different ways. You create 2 different RDDs from those textual data. If you don't cache it, this is actually what happens. That parent gets replaced. RDD is just a program. So it tells Spark how to get data, what to do with it once it runs. So if you don't cache data, this is what happens. It just re-executes the same RDD 2 times. If it's cached, then the second time it will fetch the pre-computed data from the memory. So that's kind of basic thing that you should do. But you should also unprocessed data once you no longer need it. So you might think that this is the solution, but actually no. If you do this, RDDs are lazy. So if you do this, you will just say Spark. None of these RDDs would get materialized or executed, computed. until you execute an action on one of them. So if you just do this, you would say to the parent, do not cache data once you execute it, and mapped 1 and map 2, if you execute them afterwards, parent won't be cached. So you need to do something in between that unprocessed. So you have to materialize those RDDs to force the computation of them. You can just do count, for example, or map partitions or something, or you can save the data as here, whatever you need those RDDs for. Once you compute them, then you can safely call unprocessed on that parent RDD. Then it's very important in Spark to reduce shuffling. That shuffling is movement of data between partitions inside a single RDD or several of them. So as an example program, here's a program that parallelizes a local list. Parallelize distributes local array or list to the executors. And this program just creates tuples from those, for example, there are numbers. It creates tuples containing the original number and the squared number. Then it reduces those squares to the sum of all the squares per key. And then it calls map partitions, where it just maps those sums, key value pairs to some strings. Doesn't matter what exactly it does, it's just an example. And finally it calls collect, which will force the execution. Collects all the data from the executors to the driver. If it's too much data, you would get out of memory. So this is what actually happens when you execute that program. Each of those RDDs that were created, they were created by using transformations. Transformations create new RDDs from the previous ones. And each new RDD created by transformation has a link to its parent. So that creates this RDD lineage or direct acyclic graph. And there are two types of those connections to the parent. You have one-to-one connection, or also called narrow dependency, or you have shuffle dependency. Some of those transformations will necessarily create a shuffle and initiate that data exchange between partitions. And reduce by key, by its nature, has to collocate all the elements with the same key to the same partition, so they can sum the data and so on. And by the way, this is how the Spark stages, if you ever looked at the WebUI and seen those stages, jobs and stages, this is the way the stages get created. Between those shuffled dependencies are stages. So to avoid, or rather reduce shuffling, first of all, it's known that the group by key is a very expensive operation. It groups all the keys to the same partition, all the same keys. So if you just need to aggregate data later, after you group the data by key, it's much better to use the alternative aggregate by key, which will offers you to define two functions, one combiner functions. One will be executed on each partition and try to reduce the number of values for each key inside the same partition first, and then it will use the second combiner function for after the keys have been physically relocated across the partitions. So in that way, it can be, if you have many keys inside the same partition before the shuffle, that way the amount of data that will be shuffled can be reduced, depending on your distribution of data. This is actually what it does. So the first transform operation combiner will be called on each local and each partition, and then the merge will be called on the shuffle data. So you can end up inside each partition. This pre-process can reduce the amount of data in each partition before the shuffle. Then you can also use tree aggregate instead of aggregate. Spark has been using internally for implementing some of the functionalities inside Spark. They've been using tree aggregate, and they're semantically the same. You also have the two of those combiner functions. There's also this zero value, didn't go into that. They're same semantically, but tree aggregate performs better because it actually tries to do several of those reduce operations. You provide a depth, how much you want in each step of the tree aggregate. It reduces the amount of partitions by some factor. And it does that several times until it arrives to the full shuffle. And that can also help pretty much. Another way, when joining data, two RDDs, they also have to be, both of them have to be collocated on the same, their data has to be collocated on the same partitions in order to join the same keys. One trick is to use the broadcast. So you can, if you have, broadcast is a mechanism in Spark where you broadcast an RDD or a collection of data to all the executors. And then you can use those executors inside the map partition. For RDDs, you can do it like this. You have your, for example, you get your smaller RDD that fits inside your driver, and then you broadcast it to all the executors, and then you have Spark API allows you to access that broadcast variable by using value, and then you can use that map, broadcast map, to look up the keys while joining data yourself. Or in DataFrames, it's much easier. You just say broadcast smaller DataFrame, and it will automatically do the broadcast and all the logic necessary. One other tip for better performance is to use Creole serialization. You enable it by setting the Spark serializer parameter, and there's also this parameter that says if you register classes for so that Cryo knows about your classes beforehand, then it's much faster. The serialization in Cryo and vice versa is much faster. And so, but you need to register all the classes that you want to serialize with Cryo before you start using it. And it will, if you don't register all the classes, you will get some errors. But once you go through all the classes that you need to serialize, then you're good. Then for Spark SQL, several of there's an example project I'd like to use for this. It was kind of unique because it was a migration of complex job to Spark, where we moved some traditional ETL processing to Spark. And a job originally lasted for 6 days because it had to calculate several years, day by day, and each day day's results were joined by the previous day's results. So it had a dependency on the previous day, each day. So we had some 3,000 days or so, and data was read from Oracle and DB2, a large amount of Oracle and DB2 tables, and written back to Oracle. So this is a handwritten design of the tables that needed to be joined, and we had two processes like these. Those orange boxes are the original DB2 or Oracle tables, and all the others were results of joins and so on, unions. And it was really, this all needed to happen for one single day. So we need to do this 3,000 times for the whole job. So there are some tips I could share with you regarding this. First of all, this comes out of the Spark documentation. For reading data through JDBC, reading data frames, you can push filters to the database itself. You don't want to read the whole table and then filter inside Spark. You can use where filter expression to give it to the JDBC driver to execute before giving you the data. Well, that's kind of obvious, maybe. Then you should probably cache everything as much as possible, especially in our case where we had lots of tables. We wanted to cache them as much as possible because we reused the same tables again and again. We didn't want to read the data from relational tables because that was kind of really slow. So we cached them all at the start of the job, read all the data at the start. As I said, you don't want to cache the data that you won't be needing later, because sometimes there can be problems with releasing that data. You can get out-of-memory errors, although Spark should get rid of that data automatically, evict the cached blocks automatically, but sometimes it doesn't happen. So it's important to unprocess the data if you really don't need it. But caching actually is not enough. We had lots of data cached, but after a while that cached DFs we noticed that the job was getting slower, and we realized that the data was actually read from the relational database again, because those cached pages were evicted from the cache. So Spark just re-executed the program, RDD program, to read the data again. So what we did is we checkpointed each of those to HDFS. Then you have to do the count to materialize the checkpoint. And then this is how to do it with data frames. So you have to reread the data frame from the same cached RDD, kind of hack, but you cannot do it otherwise. And then what happens is if the data needs to be recalculated, it will be read, just that partition will be read from the HDFS cache, which is much quicker than to read the whole thing from the database. Then to prepare data frames for joins, we determine the relevant columns by it's the most likely to be joined by other data frames. So we try to repartition them in advance according to the joins. So this is also what we added for each of those tables. Then this is kind of important. It can happen if you have a really big execution plan inside the Catalyst optimizer. Catalyst is the optimizer for data frames. It tries to do what the database engines do and optimize, push the predicates down to databases, to Parquet files, whatever. But if you have lots of these, you can add new column to a data frame with column, and then you say the definition of that column. You can drop columns, you can select columns, and so on the data frame. Each of these creates a new data frame and actually creates a projection, so-called projection plan in Catalyst. And each of those took our Spark engine on the driver, it took several seconds. Each of those took several seconds to execute. If your starting DEF plan is really large, it can be a very long time to calculate the plan for all those projections. So you should reduce your projections to something simpler, like instead of dropping those, you can just say select all but those. Instead of doing another with column, you can say select a new column and then give your definition inside the select, and so on. So reduce those number of projections. Then one caveat, maybe not known widely, I don't know, is that data frames have 200 partitions by default. Whether you have 3 executors or 2,000 executors, it will give each data frame by default only 200 partitions. So it might be too little, too much, and you can change it with this parameter. And it's very difficult if you have all those joins to say in advance how much partitions you actually need. They're trying to do this with adaptive, to fix this with adaptive execution. Now in Spark, it's still work in progress, but I still have 6 minutes left. Okay. So another thing we did when we did all those joins and we realized it was executing serially, one after the other. So you can use several threads. You can use the same Spark context from several threads. And that's what we did, and managed to squeeze more calculations inside the same, because if you execute several jobs, they will compete for these resources inside the Spark cluster for Spark schedulers resources. So you can kind of speed up the execution this way. We created a system for synchronizing those threads. They were waiting for each other, the results from the previous data frames, and so on. And then we divided actually those multiple threads to several jobs, which I'll talk, I think, later. Yeah, okay, so you can use several Spark applications also, because if you have different parameters that apply to one part of your data frames and different parameters to the other part of the, let's say, set of data frames. And if data loads are different, we had one part of the calculations was handling much larger amount of data than the other part, so it makes sense to divide those into several applications. And it may be specific to our use case. We handle synchronization through HDFS. Then we also had notice that WebUI is eager to eat up the memory. You have all the large data frames, because it tries to visualize and debug. If you have a WebUI SQL tab there, you can see your data frames and the execution plans and so on. And it uses memory for visualizing those, preparing data for that. That's a SQL listener class, which is on by default. This is not a huge amount of memory that was occupied here, but it was really unnecessary because we didn't need that information in WebUI. So you can restrain your WebUI. You can say how many tasks to keep in memory, how many executed executions, and so on. And you can also say Catalyst makes a string, debug string for your data frames. And if the data frame calculation plan is big, then it can be really huge, that string. And if you don't need that information in production, I suggest that you set this to some really low value. So for Spark streaming, this is actually a recommended way in Spark documentation how to start up the streaming. You should use a checkpointing directory, and then when creating the Spark context, you provide this checkpointing directories. It will, if your Spark job dies, it will then, when it's restarted, it will use the data where it left off, for example, Kafka offsets and so on. So that can really be lifesaver. Then, if you have a Kerberized HBase, secured HBase, this was kind of thing that really obscure. You can specify key tab and principal, Kerberos key tab and principal for using HDFS and so on. It works out of the box, and Spark, if the key tab expires, it will automatically, the key ticket, if it expires, it will automatically use the key tab and this principal to re-login you automatically. But for HBase, you need to log in programmatically too inside your code before accessing HBase. And it also needs the HBase master's Kerberos principal for some reason, and HBase region server Kerberos principal in order to access that cluster, it needs to know the principal of the master and region server, which is kind of, I don't know. And to write data back to Kafka storage, you could, you need to open connection from each executor. You cannot open the connection from the driver and send the connection to executors because connections aren't serializable. So you need to open connection from each executors. And one naive way would be to open connection for each record that you have, which is obviously not good. You don't want to open connection for each one. And you could write partition at once, open connection, write all the data that's in one partition, then close the connection. But the much better way would be to reuse connection between tasks, and that can be done with, you can make a static connection, open it when needed, and each task that's executing on that executor would reuse the same connection if you do it right. Yeah, okay, that's it. So I'm almost out of time. If you want to know more, you can check out my book. And now to the fastest finger game. If you'd like to win a book, so these are the steps you should follow. Go to sparkinaction.com. This is a link that will redirect you to a Manning page for the book. You can say, be sure to select ebook, not the printed book, because the discount code works for ebook. Add it to the cart. Click on the cart in the upper right corner. Then enter one of these codes into the discount code field, and I'm going to give you 3, so the first 3 people will win the book. So good luck. And then click on apply and go to the checkout as usual. So thank you. If you have any questions. Okay, I guess not. Thanks again.